Okay. Okay. Welcome to the first seminar of the interdisciplinary distinguished seminar series for the spring here. I want to welcome Ali Jadbabaie to speak today. Ali got his BS at Sharif University of Technology, top school in Iran. Got his master's at the University of New Mexico, which was my alma mater, so he must be at least as smart as I am. But he was smarter and went on to get his PhD at Caltech there. He did short stints then at Yale University, and then moved to the University of Pennsylvania in Philadelphia. He and his students have won several, I will not go through and name all of them, best paper awards at several conferences here. So with that, I will then turn it over to him and let him enlighten us this afternoon.
Thank you very much, Joel, for your introduction. Thank you all for being here, and I'd like to thank Hamid for his kind invitation. I hope his brother will be well. Sorry he's not here. So I want to tell you a little bit about some of the work that my students and collaborators and I have been doing over the past 7-8 years that I broadly put it under the umbrella of information aggregation in complex networks, but as you'll see, it has starts from some flavors in control theory and robotics, and then we sort of move towards the middle of the talk to some problems in social networks and sort of decision making and in more related to the economics literature. So this is, of course, joint work with a large group of people, students, postdocs, and collaborators. And so just to give you the way we've been thinking about you hear about complex systems and complex networks a lot. And from someone with a background in systems and control, you could sort of reduce dimensionality of complexity in a cartoonish way. So don't take this too seriously. But you could reduce the dimensions of complexity roughly along two axes. One is how many things you have that you're trying to analyze or control. And these things could be roughly, agents, they could be vehicles, they could be people in a social network, they could be decision makers in an organization, they could be birds in a flock, or, for lack of a better word, they're just dynamical entities. They get inputs, they have outputs, and they make a decision that changes their behavior. So when we analyze, when we want to talk about complex systems, we could think of two ways of defining complex. One is how complicated each individual agent is. How complicated the agent that you model is. Is it even, can you even model it? And this is where a lot of, control theory in 1980s and 1990s and even 1970s was focused on. So I model my system with differential equations or difference equations. And these models, the real system is not quite what I modeled, so there are uncertainties. So I want my design or my control to be robust. So there's been a lot of work in this thing where I say in this, if you think of this as a plane, so this is high on the y-axis but low on the x-axis, because there's only one thing I need to worry about. But this thing could be awfully complicated. It could be nonlinear, uncertain, stochastic, robust. And my claim is that this community of decision and control has made quite a bit of progress in this domain. Just for fun, to show you some of the elements of this progress. This is we don't have internet here, so I'll just point you to later if you want. I forgot to log into the internet so that I show you the video. So we have a YouTube channel of our lab. There's a video of, I wish I had internet. Is it too hard to connect this to? Oh, okay. Okay, so And this one, oh, okay, great. This is easier. So I wanted to show you a few
This
minutes
video
of
presents
this.
autonomous control capabilities for a quadrotor helicopter. We use a 20-camera Vicon system and an onboard
Video.
IMU for state estimation. Here we show single, double, and triple flips. We developed a method for flying to any position in space with any reasonable velocity or pitching. We use the method to fly through windows at various angles. Here there's less than 3 inches of clearance on all sides of the quadrotor.
Okay, so I don't want to
We also fly between
much
other
time on
quadrotors.
this, but the point was to sort of tell you that when you have good sensing and you have good models, then feedback control can do a lot of interesting things. And this was a case where we have a 20-camera Vicon system in the room, so we can measure positions with very, very high accuracy. We have a good model of each individual quadrotor. And so we could do a lot of interesting autonomous things. So later on in this video and other videos, you could see, we threw a hula hoop and then the actual quadrotor goes through it. So the planning could be done in real time, and it's really fast. So okay, so this we could do a lot of interesting things in this space. But what I want to spend more time on today is, well, what happens if we are here, where the models could be, maybe they're not that complicated individually, but we have many things, and the action is in the interconnection structure, in the way that things talk to each other. It's in the sparsity of the interconnection of who can talk to whom that makes this interesting. And the system is large enough that you don't want to consider the whole thing as one big aggregate dynamical system because it's too big to do the computation, and also you don't have access to all the information because the system is spatially distributed, the information is local, and you would like to do generate interesting behaviors or analyze interesting behaviors that are global, but you want to do this with local information exchange. So I'll use flocking, synchronization, and consensus as examples of such a behavior. And the hope is that if we understand this well, and if we understand this well, then we could say something about things further off. Okay, but as I said, my talk will be mostly on the thing on the right. So this is what has happened over the past 10 years in systems and control. A lot of focus has shifted from doing things here to doing things in here. And some things up here as well. Okay, so independently of this, there's also been, in our discipline and many others nearby, there's this interest in this buzzword of network science. So we see networks everywhere around us, from the internet to services that run on the internet, to the power grid, the network of economic entities, biological networks, metabolic networks, and you name it, there are networks everywhere. And we don't have quite a good understanding of what are the effects of the network structure of things on the behavior of the individuals in this aggregate system. So Army, a few years ago, commissioned a study to National Research Council to issue a report asking the question, is there such a thing as network science? Is it a science? Or is it just a fragmented collection of things that are in certain disciplines and they don't aggregate very well? And so they asked to say, okay, what is it? Is this something Army should spend money and effort, studying, supporting, or not? And the answer was an overwhelming yes, that this is an important thing. We need to understand dynamic spatial location, allocation, and information propagation in networks. And we need to be able to develop abstractions that transcend individual disciplines, and to be able to use this to see, okay, what's this impact of this network structure in a metabolic network, but what does the same motifs show up in, let's say, a wireless communication scenario? What happens here when I want to do a sort of a distributed resource allocation mechanism in an economic network, and so forth. So there's been a lot of activity going on in here, and I would like to connect some of these two things together. And my focus, the focus of the things that I present, are mostly on the top bullets shown. Okay, so I mentioned aggregation in the title. This is a topic that has been studied across many disciplines, starting from physics to dynamical systems, to evolutionary biology, to computer graphics, you name it. I mean, these things are all over the place. And the focus of the study is very simple. How do you study emergence of synchronization or consensus, or what in biology you might call a flocking behavior, among different individual entities that are capable of only information exchange and communicating with their nearest neighbors? So you have a bunch of dynamical entities. Think of them as birds or robots, or whatever you like. And they can only talk to, they're range limited. They can only talk to a few people around them. And they'd like to exchange decisions so that they all agree on what to do collectively together, how they should do their motion. The simplest, primitive of motion you could think of is to have sort of what we call a rectilinear formation, or move in aggregate as a swarm or a flock. So how would you model such a thing? Turns out the studies of this in computer graphics happened in 1980s. In mid-90s, some statistical physicists actually proposed a simple model of study of this phenomena, where you model each agent as a point particle moving with constant speed, and then you're trying to exchange information with your neighbors to align sort of the direction of the velocity vector. And they show with the simple model that if you average locally your direction with that of your neighbors, eventually interesting things happen, and they do that with simulations. So later on, similar, they've actually, approaches were used in crowd control. They made the cover of a lot of these popular sciencey magazines. And then, of course, there's this independent issue of synchronization, which has a similar flavor. So you have individual oscillators oscillating at different frequencies. Think of this as people clapping in a concert hall. When the show ends, people start clapping. Everybody is clapping at some frequency, but very soon they all lock together. And the way you do it is that you listen to the people around you. If you're going faster, you slow down. If you're going slower, you speed up. So you want to know, how does this aggregation of local information to something interesting and global actually happens? And a lot of what has happened prior was mostly insightful, sometimes simulations, but nothing that you would call that mathematical, that will give you interesting insights of how and why these things are happening. So this is what I've spent a lot of time on, to study these type of problems and relate them to things like bird flocking, to coordination and coverage control, to resource allocation in algorithms, and to attitude synchronization of satellites, formation control, and whatnot. And more recently, I've become interested in similar style of problems, but now more focused in the social and economic domain. So you could have, it turns out that a lot of the math starts similar. So you want to understand how things like epidemics and pandemics propagate, network, how local decisions suddenly take over, how fashions and bubbles and bank runs propagate, and so forth. We're not quite there yet, but we have some interesting insights that at least one can formalize some aspects of these issues. But going back to now trying to make this a little bit more formal, we studied this problem of flocking or consensus and velocity a while ago, and this received a lot of attention. So this was interesting because the model that these physicists came up with was simple enough to allow you to do analysis, but complicated enough to give you something about the real thing. And it was just the right zone. So think of these individuals as particles or robots. They all move in this plane or in 3D. Let's make things simple and have them move in plane. And they can all talk to, so this is like the IF agent. They all move with a constant speed. And the thing that we're trying to control is their heading. So there's only an angle that is of interest. Of course, they have positions, but they aggregate their angles with the information of their neighbors, and then they take one step along that angle that they computed. Okay, this is a very simple, point robot kinematic model of an underactuated robot, or if you like, a unicycle model. Except, you can do it both in discrete and continuous time. The interesting twist is that we're going to say, okay, whoever's within some radius, we have reliable access to their information, and if they're outside, we don't. And of course, you see right away that I'm sort of abstracting out all the interesting communication issues. So this is not a good model for the details of the communication, but it's just this crude zeroth order model of us trying to understand how the interconnection structure affects the overall dynamics. Okay, so the central question here, like many other problems that I'll mention, is how does global behavior or herding or schooling or flocking is achieved from local information? Okay, so how do you do this? Well, the model is very intuitive. You take the heading of each agent, you get the heading of your neighbors, you find the argument of the sum of the sines of the angles divided by sum of the cosines. And if you do a simple change of coordinates, this ends up being nothing but just a weighted averaging of another quantity. Okay? So the issue is that if you want to get everybody to aggregate their heading information, all you have to do is just to average your heading with that of your neighbor. But the interesting twist is that the set of neighbors over which you're doing this averaging changes over time. Why does this set change over time? Because I'm doing this averaging now, and then I take one step, and I move. So now somebody else is my neighbor. Okay? So the network, if I start with a network, I won't necessarily get the same. I could write this update in discrete time this way, or I could write it in continuous time down here. And if I want to write it in vector form, this is just a linear differential equation. But it's a switched linear system because every time there's a change in network, I get a discontinuous change in the dynamics. And I could write it in terms of matrices associated with this underlying proximity graph. This D is the degree matrix. It's a diagonal matrix of degrees or valences. And this A is the adjacency matrix. So it's the 0, 1 matrix that says who's neighbor. Or it could be a weighted adjacency. Doesn't matter. Okay, so how does this work? So there's something interesting going on here. Because on the one hand, this is a problem in the dynamical systems domain. You have this aggregate state. You want to study some sort of stability for the behavior of the state. Except you're not interested in stability to a point. You're interested in stability to a set. And the set that you want to understand stability towards to is this diagonal of your configuration space where all the states are the same. Okay? So you want to see whether this set attracts or not. And the other thing is that there is a connection between the combinatorics of the interconnection represented by that graph and the stability of this underlying dynamical system in the sense that I just mentioned. And this is what we sort of characterize in our 2002 paper. What we showed was that if there are sequences of bounded non-overlapping time intervals such that over any interval of that time, the network of agents is what we coined as jointly connected, then all agents will asymptotically reach, and in fact exponentially reach consensus. What do we mean by jointly connected? What we mean is that whenever your graph changes, think of that as another graph on the same set of nodes. So think of the graph change as a result of motion as the blinking of edges of these graphs. Put all the graphs on top of each other. If there is a finite sequence over which these graphs correspond to a connected graph, when you put them on top of each other, then this process will converge. And you can do many things on this. For example, what's the rate? It relates to how quickly you get a connected graph, and many others. So here's a cartoon picture of this. So I have the gray graph, then I have the green graph, then I get the red graph, and then in 1 second I don't see any change, but in the next event change I get the blue graph, and over 4 steps I got a connected graph. So if this thing persists and happens, even though the switching might not stop at all, then things work out. For an example, a special case of this is when the graph is connected once in a while. So that's a special case. That if there's infinitely often connectivity, then things will work. And this has actually led to lots of interesting extensions. You could do this in continuous time, as I showed earlier, in which case you have the switch system and the condition would still be the same. You could do this for certain nonlinear updates. So instead of saying averaging, your update could be any nonlinear map that assigns a point in the interior of the convex hull of the value of yourself and your neighbors. So in a way, it's kind of like an average. It doesn't have to be averaging per se. Okay, so then this was the case where you had no inertia. Well, what happens if we go to second order? We want to make the model more complicated. So now we want to also add collision avoidance. So if you add collision avoidance, then you would want to say, okay, I want to make sure that these agents don't get too far and they don't get too close to each other. We did a series of papers from 2003 to 2007 describing such a model where you have the second order, sort of the so-called double integrator dynamics. That's just nothing but F equal to ma. So R is your position, R dot is the velocity, V dot is the acceleration, assuming unit mass here. And we're saying the control effort has two parts. The one part is the alignment part, which is very similar to the velocity alignment part that we saw earlier. There's a second part that is a collision avoidance and attraction part that is based on gradient of a certain potential. And then our results were also extended by Cocker and Smale by constructing distance-dependent adjacencies. But the potential we used was a sort of a Leonard-Jones type potential, which is the type of potential people in molecular dynamics study a lot. You could think of this potential does what we want. So something that is like this. Basically, you want a repulsive force for certain distances, and then you want an attractive force for certain other distances, and you want this to flatten out so that agents don't affect each other after a while. And in fact, biologists tell us that this is a pretty good, this type of a zone model is what they think happens in both bird flocking and fish schooling. That they have a repulsion force, they have a attraction force, and then after a while they don't affect each other that much. Now, of course, if you want to make a strict flattening of the potential, which means the force goes to zero in a finite time, then you'll have this issue that you have this discontinuous change in your forces because when somebody comes into your range, suddenly you have a discontinuous change. So we've also taken care of these discontinuities via some non-smooth analysis, which I won't get into here. You could also add other potential forces that sort of are designed to maintain connectivity. You could interpret loss of connectivity in this multi-robot system as an obstacle. So you could generate a repulsive force if you see that the agents are breaking away. Then another thing we decided to do was to say, well, what if we don't have access to the heading information? If we want to use a vision-based system to align these robots together, or if we want to really model the way fish and birds do it, it's not necessarily based on communication of the velocity information, but it could be based on visual sensing. And so we showed in a series of papers that, in fact, with visual cues, we can reproduce similar results. And the information we needed for doing this was the bearing, which is basically the unit vector along the vector that connects the two robots together in their own coordinates. We need the optical flow, which is the derivative of bearing, and we need the loom or time to collision. And with these three quantities, we showed that we could actually reproduce the same results. Interestingly, and we didn't know this, but turns out that that optical flow measurements have been documented in many flying species. Loom measurements have been documented in birds and in fish, and also in flies. This is very critical in doing their cicada maneuvers, which is these very high angle of attack turns. Okay, so we did this also. It turns out you could do exactly similar type of controllers, but instead of measuring velocity information, you're just measuring these ones. Okay, so a related problem to this is that of synchronization that I mentioned earlier. This has been a problem studied in one form or other for hundreds of years. And the idea is you want to figure out, if you have a bunch of oscillating entities that are oscillating at nearby frequencies, how can you lock them together globally with just exchanging phase information in a local way? This is, many people have worked on this and across many disciplines, from RF circuits in the context of injection locking, in Josephson junctions, in semiconductors, in mathematical physics and neuroscience. This has been studied quite a bit. And there's a sort of a quintessential model called the Kuramoto model that again has the same type of a flavor that everybody has looked at. What people have looked at is this all-to-all Kuramoto model, which is basically, think of each node in this graph as an oscillator oscillating with some frequency omega I. And then you would frequency lock these oscillators together. The edge tells you who you can talk to whom. The standard model studied in physics is the all-to-all connection. So here you have the all-to-all connection, so everybody's connected to everyone. So this model does not correspond to this graph. What you do is you feed back the sign of the phase difference between yourself and your neighbors. And this acts like sort of almost like a proportional controller. It basically says, if you're going too fast, slow down. If you're going slower than the others, speed up. And if you think about it, this is sort of the nonlinear model that I showed you earlier. You have to stare at it for a few minutes to see that. But what we did is we said, well, this is the all-to-all model. We could actually put a graph structure there and write the same model for basically individuals with sparsely connected interconnections. And we basically showed that we can characterize the onset of synchronization, find the value of the gain in terms of the properties of the network that allows you for global synchrony to happen. And I'm going a little bit slow. I think I should speed up. We generalized this model to the case where you have not just the sign mapping, but general nonlinear maps with certain properties. The network could switch, and you could have communication delays. So the information from the neighboring nodes does not come at the same time. There's a delay. As long as the delay is finite and constant, we showed that exact similar results hold. I can skip this. Okay, let me skip this part too. Okay, so I mentioned a lot about consensus problems, but then you might ask, what is the value that we all agree on in this process? What do we agree upon? Now, when the network changes, the value that you converge to is actually a complicated function of the way the network changes and the initial values. So it's not easy to characterize it. In the particular case where the network changes randomly, we've been able to characterize this. But in general, you might ask, how am I, if I'm especially interested more in the decision-making side of things and filtering side of things, how can I aggregate local information to get some global understanding and aggregate it sort of in the correct rational fashion? So there are few special cases that this type of an aggregation actually gives you the correct answer. One is when you have essentially linear models, linear measurement models. So you think of your networks as as sort of representing measurements, and the edges would represent whose information you can exchange with whom. And you have a linear model with Gaussian noise. It's just a simple scalar model. So every sensor just measures the corrupted version, the additively corrupted version of the quantity of interest. It's the simplest possible case. Okay? In that case, well, we all know the maximum likelihood solution is just the average of the measurements. Okay? And you could think of this algorithm as a way of computing this average in a distributed fashion even when your network changes. So of doing this, so you do one measurement, and then the nodes talk to each other even if the network changes. And if this connectivity conditions I showed you earlier hold, then everybody reaches agreement to the average, which is the maximum likelihood value. This is one example whether when the consensus scheme aggregates the information correctly. Another scheme is where you want to do this in the context of opinion dynamics. You're trying to measure some parameter, and your measurement is sort of the, again, additively corrupted version of that parameter. And so you talk to your neighbors about your measurements, and then you aggregate it in this simple, by myopically averaging way. Now, to someone who's working on information aggregation and sort of especially more from the econ side of things, this is an awfully stupid thing to do, because you're reacting at every iteration to the last thing that you heard. Okay? If 3 people tell you the same thing, right, you give it 3 times the weight. You don't look to see whether the source of this information was the same person that is spreading some rumor to you. So you give it 3 times the weight. Okay? So yes, you reach agreement with this scheme, but do you reach agreement on the correct value? So Matthew Jackson and is an economist at Stanford and Ben Golub, using some simple analysis of this model, they basically showed that when law of large numbers kicks in, when the network is very large, okay, then even though you're being myopic and naive, this scheme of aggregating the last thing you heard by averaging with your neighbors actually works, provided that the thing that you were trying to estimate was just additively corrupted by zero mean noise. Because you converge to an average, and the average goes to the mean of the distribution when your network goes to infinity. So they call this sort of the wisdom of crowds kicking in, meaning that if the network becomes large, even though you're doing something simple, then everything works out. And so this is what basically their model. So this is some opinion or some decision that you're interested in. And you get measurements of this opinion or decision in a corrupted way. So SI is my measurement. Theta star is what I like to see, but I don't see theta star. I see theta star corrupted by this noise epsilon. So I run this. I start with this my measurement. Everybody does that. And then we all do this repeated averaging with our neighbors. And what happens is that as n goes to infinity, if I don't have in my net, there's an if here. The if is that if I don't have anybody that is overtly opinionated, that sticks to what they think is the correct answer. So if I have somebody who doesn't follow the protocol, who keeps with the value that they had, that messes things up. What you need to have is that everybody should follow the protocol. Everybody averages their value with their neighbors. Eventually, law of large number kicks in, and everybody gets the correct value. Okay. But if you have people that stick to their opinion and don't change their value, then they could sort of hijack the estimate, and you won't get the right answer. Okay, so this is a very special case and only kicks in this naive scheme when the network is very large. How can you aggregate this type of information in general? Well, the rational way of aggregating information is to follow the Bayes rule. At least that's what the Bayesians like to think. So how do you use Bayes rule in the context of aggregation or rational, what you might call learning of a parameter? This is what you do. Excuse me. So imagine you have a finite set of possible states of the world. So you want to know whether I want to vote for candidate A or B or KFC, or if I want to go to Chinese or Indian restaurant, or if I want to get an iPhone or an Android phone. So this is a finite set. And the correct set answer based on the measurements is one of these finitely or even countably many states. Okay, so I have a rational agent, and I get some noisy signal about the quality of this product or this restaurant or whatever. This is the signal. The information is in the signal. I don't get the signal, and I get this likelihood function, which is this parameter-dependent distribution that tells me how the signal relates to the parameter. So for example, in the linear model with Gaussian noise, this likelihood function would be very easy to write. Okay? Then what do? Well, you start with some probability distribution on a discrete probability distribution on the possible states as your prior. So you say, okay, I don't have any bias, so I'm 50-50 towards Android or iPhone. Then as you get these measurements, you deform this probability distribution with Bayes' rule as the new information comes in. The new information comes in the form of this signal, and then you basically run the Bayes' rule, which basically says your belief at the next time is the belief that you had at the previous time times the likelihood divided by this normalized prediction of the forecast of the future. This is the usual Bayes' rule you learn in the probability course. I wrote it in a slightly different way. So you're saying you could think of this as mu of theta given S is at the next time is mu of theta times L of S over theta over L of S given theta j, mu of theta j, summed up over it. That's the denominator of the Bayes rule. So this is just the standard Bayes rule you see in probability. Okay. So this is a classical result in statistics by Blackwell and Dubin from early 60s that basically says you have a finite set, and if you're not totally clueless to put 0 probability on the true state, then eventually using a martingale argument, you can prove that this distribution becomes, you go to a stationary point, and the forecasts become eventually correct. What does that mean? That means that this ratio becomes 1. Okay? Furthermore, if you don't have any identification problem, if you don't have any observability issues in your model, then you can show that this distribution becomes a delta function on the true state. So you learn the truth, basically. Okay? So what people have been trying to do in many communities is to see how do you extend this to a network setting. So we could do that. We know how to aggregate information in a Bayesian way that is rational when I have one agent and signals are coming in. I start with a prior. I compute the posterior with the Bayes rule. I show that this is a martingale, and then almost surely, asymptotically, I converge to the true state. In fact, you can prove that if you have a discrete state space, this convergence will be exponential. The rate will have something to do with the Kullback-Leibler distance between the true distribution, the likelihood at the true state, and the likelihood at the false state. Okay? Okay. But this is now tricky to do in a network setting. Why is it tricky to do in a network setting? So imagine you want to reproduce the same thing in a network setting. When I say in a network setting, there shouldn't be any cheating here, meaning that you are only allowed access to the information of your neighbors. You don't know what the network is. You only see who your neighbors are, and you see, and they are willing to communicate with you their beliefs. That's all you see. Okay? And very easily you realize after a few minutes of staring at this that you can't run the Bayes rule that way. And here's the reason. So you have different agents. So now you have, at time t, the belief of agent I on the state theta being the true state. This is the probability that theta is theta star given the filtration. And this is just a fancy way of saying everything else that we've seen so far. So this filtration is the sigma field generated by all these signals that I've observed before. and the beliefs of my neighbors from time 0 up to now. Okay? So you realize that this is a huge thing, and I can't run the inference just based on that information, because I need to make rational deduction about everybody's beliefs based on only seeing my neighbor's beliefs. It's not, you can't decentralize or distribute the computation of this update. And the reason is that you don't have a complete network information. You only see your neighbors. Okay? See, this is the issue that you did not have in the naive update. In the simple case where you were averaging, you didn't care what everybody else was doing. The law of large number took care of things. You converged to the mean of the distribution, and then you were fine. But here, you would have to distinguish if 3 people are telling you the same thing. You would have to look one step back if you want to do a rational update to see whether that information is coming from the same thing. What Bayes' rule does is distills the new information from the old one, so that you're not using the same recycled old information. You don't know anything about other people's signal structure and their observability model, and also the issue is that the higher order beliefs matter. You fall into this game of I know that you know that I know that you know that I know that you know, and that goes forever. These are called higher order beliefs. And more importantly, as I said, you don't know what source of information of these other agents is because you only see one half of it. Okay, so this has been something that people in many communities are working on to try to extend this type of, you want to call it, and people call it different things. You want to call it Bayesian learning, you want to call it filtering, estimation, detection. You want to do this in a decentralized way and in a network setting. And again, the easy way to cheat is that to flood all the information to one node, aggregate everything in that one node, and have that one node have access to all the signals, and that guy runs the Bayes rule. So you could do that, but we want to disallow that so that the information exchange is only local. We want the information to diffuse locally between agents. How do we do this? So again, in this cartoon, same cartoon, now I have 2 camps. This is the Economist Camp. Everything has to be rational, otherwise I won't talk to you. The dogma is that everything has to be Bayes' rule. If I want to do Bayes' rule, I can only do if I have 2 firms or at most 3, and I can't really handle all the data. Then there is this analog of the consensus flocking scheme, which you can call naive learning, which is based on this repeated averaging or just some repeated local update. So here, you don't have rationality because your update is very myopic, but it's simple. Here you have rationality, but doesn't quite extend the network setting. So I would like to, what we're doing here is we're proposing something that is in between. So I hope I can convince you that that's interesting. So I want to give you a, yes?
Propagation.
So the Bayes rule part of it is, but it's not really belief propagation, because in belief propagation what you have is that you're trying to learn, you have a distribution, and this distribution is factored based on certain dependencies. And the graph represents how this likelihood function is factored through the dependencies between nodes. The edges in my graph don't mean that. They mean something different. The edges in my graph means who can talk to whom. It's not how the likelihood function is factored. So you could put belief propagation on top of this, or graphical models on top of this, but my graph is not a graphical model. It's a model and a graph, but it's not a graphical. It's not a graphical. I'll get back to that towards the end. Okay, so I want to come up with a local and computationally tractable update, which gives me which reproduces the consensus, but gives me consensus in a rational way on the true state. And this is the trick that we've used. This is the work of my former student, who's a postdoc now at MIT, and the fellow economist Alvaro Sandroni. So we came up with a scheme where the agent is Bayesian when it comes to her own observation, but follows the naive simple averaging rule when it's aggregating the information from neighbors. Okay? So strictly speaking, it's a non-Bayesian update, but it's only Bayesian with respect to the private observation. So let me be more detailed about this. Okay, this notation is fairly standard, and hopefully it's easy to understand. So you have a bunch of nodes. These are agents that get the observation. You have a directed network that represents who's talking to whom. And as I said, this is not the way necessarily that your likelihood factors. This is not that graph. You have a finite parameter space, possible states of the world, and the true state is one of these. And then you have these signals that you get. So different people get different signals. These signals could be correlated at each instant, but the key thing for our result is that they are independent over time. So they're IID. They're independent and they're identically distributed. There is a global likelihood function, L of S over T. Okay? And there's a local likelihood function. Okay? Which is the ith marginal, and I have access to this. In the belief propagation or graphical models, the graph represents how this L of S over given theta factors into different products. It shows you, it keeps tracks and bookkeeps the dependencies between different nodes. We don't have that here. We don't have that information. So all I know is I have my own marginal. Okay, and here's where the beliefs go. So I have my own marginal. I update my own belief. Yes?
What would be the justification for the signals being IID? Won't you assume that they would be very much dependent instead of independent?
No, the signals between agents could be correlated. But over time, they're IID. Okay? Well, you need to make some assumption to make the things work. But the key thing is we don't require the signals because, you know, if the people are nearby, the chances are the signals they get are correlated. Okay. But we're not using that correlation information up to now. Okay? So everybody starts with a prior. There is my belief, and this is sort of the denominator of the Bayes rule that I would use to forecast for agent I the next observation profile. Okay. So now I could have, like before, I could have two notions of learning. And this is following the standard notation in game theory and learning literature by Kalai and Leher. And basically, you could have one which you would call weak merging of opinions. If you know, from a adaptive signal processing or control side, you could say this is the part where I match the outputs. I match the observations. And then in this case, a stronger notion is what we call asymptotic learning, which is you have the right persistence conditions, and not only you can match the outputs, but you can now predict what state produced that output. Okay? Because I might be able to have this produce the same likelihood for the weather as the true state, but there might be many states that produce the same prediction of the future. So this is the stronger thing that we're looking for. This means that everybody's belief becomes a delta function on truth. So before we were reaching consensus on scalars, here we're reaching consensus on functions, or in this case, discrete functions that are vectors, probability distributions. Okay, so this is our update. So it's a generalization of the single agent Bayesian update and the naive consensus update, which was based on average, repeated local averaging. It basically says first come up with an intermediate belief, which is Bayes' rule applied to your own private observation. So I am the ith agent. I start with a prior. I have my own marginal, Li, and I pretend nobody else is present. And I have my own signal, so I do my inference. Now, here's where you would ask the question, if I have my own marginal, then why on earth am I bothering even to listen to anybody else? So I just use this update, and then I'd learn. And the reason you would want to do this is that you have identification issues. If you learn on your own, nobody's signal on their own is rich enough to narrow the support from all possible states to the true state. So this is, if I want to make the analogy to the linear case, imagine that you have a large model that you're trying to observe. Each sensor picks only one state. So it's observable with respect to that one state. Okay? Unless everybody talks to everyone, you don't get the full picture. So this is the situation here. I have each node I only sees SI. And the information in SI is not rich enough to allow him to get the delta function that we want. Okay? It might reduce this as you deform this probability distribution with Bayes' rule. It might support the distribution, it might make the support smaller a little bit. So for example, it might say, okay, if I learn on my own, I will figure out that theta 2 and theta 3 and theta 5 are not the true states. But I wouldn't be able to distinguish between the other states. And this is why you need the information from your neighbors. So you could think of this model in two ways. You could think of it in a design way, as an algorithm for doing this sort of distributed inference or estimation. Or you could think of it if you're, on the more social science side of things. You could say, I would like to be rational with respect to my own observation, but I'm under influence from the belief of my neighbors. So I'm incorporating the belief of my neighbors in a naive, irrational way. There's two ways to sort of view this, depending on your point of view. So this Bayesian posterior was just the intermediate belief. Now what I do is I take this intermediate belief and take a convex combination, or an average, of that intermediate belief with the belief of my neighbors. So I take these probability vectors, and then I average these probability vectors. I'm guaranteed to end up with a probability vector. Okay? Now you'll see that this is a generalization of a single agent Bayesian learning, which is when you have no neighbors or you ignore your neighbors. And it's the generalization of the naive learning when your own signal is not informative at all. So you're just naively averaging. Okay, so here's now the full update. So I write the Bayesian part with respect to the neighbors and the linear combination of beliefs of neighbors. And this update is now local and tractable. And it doesn't care what's outside my immediate neighbor. Okay. So our first result is that if the social network is strongly connected, and if each agent has self-confidence in its own update, so you don't ignore your own update, your own belief, and there is somebody in the network that is not totally clueless about the truth. So not everybody needs to have a positive prior on truth. It's enough to have one guy have a positive prior on. Then everybody's forecast will be eventually almost surely correct. This means that the agents will make accurate predictions about the future. But now the tricky question is there enough observability globally so that you nail down the true state, not just update the beliefs? Let me skip this. This is how the update is generated. Okay. Now, to make sure to sort of solve the observability issue, you can have two scenarios. One easy scenario is to put a restriction on the inputs that stacks the deck in favor of truth. So here, we made an assumption that the IID signals that keep coming, there exists a signal that will realize with non-zero probability, so that every time tells you a little bit about the true state. Okay? Basically, that says the likelihood of having this signal if the state were theta over the likelihood of that signal given theta star is smaller than 1. Right? Because what are we saying in the end? We're saying that the signals, the observations that we get, should eventually guide us towards the true state. But here we're saying every time we get a good signal with non-zero probability. But this is too restrictive. If I want to relate this to the earlier part of the talk in terms of connectivity, this is kind of like assuming that my network is every time connected. Every time something good happens. And so 8 months and a lot of computations later, we were able to actually extend this and to show that that actually was not necessary. We knew that was not necessary, but we couldn't prove the stronger result. Very recently, we were able to prove the following. That actually, you don't need to make an assumption that everything is stacked in favor of truth. That eventually there will be a long enough profile, okay, that the likelihood of observing a k-length sequence of signals under the truth would be more than under the non-true states. Okay? So this will happen automatically. Because, why would this happen automatically? Because the true state is distinguishable from the non-true states globally. Note that if you cannot distinguish the true state from the non-true states globally, then there's no hope in doing it locally. So you need to assume that globally there's enough information to solve the inference. Okay? So here we show that, in fact, this condition is already satisfied. There will be a long enough sequence of signals that, long enough but finite, that makes, that because the signal is globally identifiable, the state is globally identifiable, there will be a signal profile that will lead you towards the true state. So now we have this result that says, basically, all agents will get equal beliefs. So all the probability distributions will be the same. And finally, that we can make inference about every other agent's signal. You see, in the end, all the information was in the signal. What we were trying to do is to replicate the situation that you have one node who has access to all the signals and runs the Bayes rule. But because we didn't have all the signals, we said we have a network, we're getting a signal, and we're getting different people's beliefs. People are getting signals, and they're processing those signals through their beliefs. Okay. And what we're showing here is that in a connected network, the beliefs can diffuse in the network in the right way to make this inference work as if I'm running the Bayes rule. So I'm running the true Bayes rule, but at the same time, I'm not running the true Bayes rule. I'm reproducing, asymptotically reproducing the result as if I were to run the true Bayes rule. So now I put everything together, and this is the main result. That if you have a connected social network, and everybody has a positive self-reliance, otherwise you'll forget someone's belief if you don't have positive self-reliance. And if there's a positive prior on truth, and globally, the true state is identifiable. There is no state that is, from a global point of view, is equivalent to the true state. Then all agents will reach consensus on this. Their belief will reach consensus on the true state. And sort of here's a simple example of how this would happen. So imagine you have 7 nodes. The true state is state 1. The signals are head and tail. You're trying to figure out the bias of a coin. And the likelihood function of a head, given theta, is such that for each node, it allows them to figure out whether they're it or not. Meaning that whether node 1 is the true state, node 2 has the true state, or has the index of the true state, or so. So node 1 can only figure out on its own that whether the true state is theta 1 or not. Node 2 can figure out whether the true state is theta 2 or not. Individually, they can't figure out uniquely what the true state is. But when they run this process, because information diffuses in this strongly connected network, they can finally figure things out. And the rate, it's awfully more complicated than the single agent Bayesian to compute, but you can actually show that it's exponential. And the rate will have to qualify that. This is the rate based on the linearization. And actually, you have to jump through a lot of hoops to convince yourself that you're allowed to linearize this random dynamical system and use the rate of the linearization to say something about the rate of the nonlinear system. So the first method of Lyapunov that we take for granted in deterministic dynamical systems doesn't necessarily extend very easily to the non-deterministic case. There are all sorts of bells and whistles attached, but turns out things work out here. We need to be strongly connected, and in fact, you can construct a simple example of a two-node with an edge between them that goes one way, in which the process wouldn't even converge. This would happen if the information structure of different nodes are different, meaning that one node on its own, one node is just running the Bayes rule fully, but it doesn't have good observability. The other node has good observability, but is running this scheme. Okay? The Bayesian node, because it doesn't have good observability, is misleading this other node. If this other node cannot correct the Bayesian node, then the scheme will not converge. So you need strong connectivity for this to work, meaning that there has to be a directed path from any node to any other.
And tail example that you showed for the ring graph would be applicable for a star graph as well?
Well, it depends on where you put the edges. If the edges in the star graph go both ways, yes. Okay. So this is sort of a cartoon that summarizes everything. So this basically shows that you can have in your network different people that have different characteristics and still have this method work. Okay, so you have one agent or that puts zero probability on the true state, is very opinionated, and doesn't listen to anybody else. So doesn't take any edge back. You have one agent that is sort of the missing link that completes the observability. And you have a separate agent that puts a positive prior on truth. So this network effect allows you for different people to have different parts of the puzzle. And the communication between them makes things work. If you don't have an edge back to influence this guy, well, nothing will work. But if you can, even with a small weight, influence this other node to make the network strongly connected, then eventually everybody will converge on the true state. But, of course, if the less connected the network is, the longer this will take to converge. And let me just thank the sponsors and stop here. Thank you very much. Yes.
So how robust is the scheme to attacks like presenting nodes? You show the example that maybe one node is malicious and it's fine. Have you studied to what extent the nodes?
Okay, we don't quite know the answer to that, but we suspect that it very much depends on where that misbehaving node is. The location of that node in the network and how connected it is to others.
Have you consider a problem like percentage of nodes?
Not yet, no. This is fairly recent, so we haven't. We just completed the rate analysis to prove actually that the convergence rate is exponential. So,
a quick question on the first part of the talk where
Yes.
you were talking about the synchronization problem.
Yes.
So the potential energy function that you define, you take the gradient of the potential and you feed it back through the graph, I guess.
All right, so that's what's for the flocking part.
Right.
Okay.
So do you use the potential energy function as a means of some Lyapunov function, or?
Well, so yes, so turns out that the Lyapunov function for the problem becomes the sum of the potential and the kinetic energy.
Right. So my question was that generally for proving global asymptotic stability, we need the the Lyapunov function to be radially unbounded, right? But in your case, the potential was sort of becoming.
Oh, very good point. Okay, so we have two analyses. One is for the case that we use this Lennard-Jones potential. In that case, the problem is not quite decentralized because the potential grows logarithmically. It never goes to 0. Okay, so it kind of has the property you need. The other case where the potential remains flat, we use sort of Filipov solutions of differential equations and non-smooth analysis, and the result is quite messy, but you can still do it. But there's like a lot of math in between, a lot of headache just because of the discontinuities that results in when you smooth things out, the math becomes much simpler. I mean, just for example, one key issue is in all of these results, the Lyapunov function derivative is not negative definite. So you have to use Lassalle's invariance principle. Lassalle's invariance principle doesn't extend to vector fields that are switching very easily. So you need to redo Lasalle.
Wasn't there a similar paper by, Murat was my advisor, so...
Yes, yes. Yes.
Lyrical systems which are defined by first and
yes, yes. So I'm aware of. So we did, in fact, Murat's work actually improves on our result a little bit, or actually, it sort of provides sort of from an adaptive control perspective, reproduces the same, and the connectivity condition reproduces the connectivity condition that Moreau showed, which I referenced. Yes.
How about experimental, physical experimentation with networks? Have you done?
Right. So in this vehicle lab that I showed earlier, we've done simple experimentations on flocking of. It's very hard to maintain large groups in
small spaces.
So we've done experiments of a parallel formation, things moving in parallel, and things moving and constructing circular formations between 7 and 8 robots. And in fact, we have tested the vision-based formation control that I showed you earlier with optical flow and time to collision and so forth with 5 robots. Yes, yeah, we've done that in experiments.
Really sparse data. Sparse. Only receive signal strength from the neighbor to the robot.
So we have. My colleague Vijay has a student who's John Fink, who's looking at getting sort of the radio signal strength map and sort of estimating that map to use this. So we're not quite doing what you said, but we're making the communication model. The disk model is really a toy model for communication. Right. So what we're doing is we're getting this full rate model, and we're getting the fading effects and things like that into the picture as well. But we're not fully done yet, I would say.
That's what we're working on.
Right. So we're trying to do that as well. Okay. Thank you very much.